Good day, class, and welcome to another lesson in organic chemistry. Last class, we started treating alcohols, and we said there exist three main types of aliphatic alcohols: primary, secondary, and tertiary alcohols. And also, we said there exists aromatic alcohol, which is phenol. And non-aromatic alcohols are array substituents of aliphatic alcohols in which the hydroxy group is separated from the benzene ring by at least one methyl group. We also went further to see how we could obtain alcohols from the laboratory. We said, first, by reduction of aldehydes, ketones, carboxylic acids, and esters using lithium aluminum tetrahydride in dry ether, and then water. And another method was hydration of alkenes using phosphoric acid at high temperature and pressure, and also using concentrated sulfuric acid and water. Using potassium permanganate is going to yield us a diol, and also in the presence of hydrogen peroxide and osmium tetraoxide as catalysts, we are going to have a diol as well. We looked at the physical properties of alcohols, that alcohols, the lower alcohols, are colorless liquids, and alcohols have high melting and boiling points than alkanes of comparable relative molecular mass, and also than other compounds with same relative molecular mass. And this is so due to hydrogen bonding between alcohol molecules. Today, we are going to be looking at aromatic alcohols, which is phenol. When the hydroxy group is attached to the benzene ring, the compound is called phenol. Like you can see, the hydroxy group is attached to the benzene ring. The compound is called phenol. When the hydroxy group is attached to a side chain, on the benzene ring, then it is called a phenyl alcohol. Like you can see there, we have naphthalene, otherwise known as 2-naphthol, 4-methylphenol, 1-phenylethanol, phenylmethanol, 2-phenylethanol, and benzene 1,4-diol. Now we'll be looking at the preparation of phenol. The first method by which we can obtain phenol here is by oxidation of phenylamine. Phenylamine being oxidized using sodium nitrite and hydrogen ion, that is in an acid medium less than 10 degrees Celsius, is going to give us phenol. And also by hydrolysis of halobenzene, for example chlorobenzene, reacting with concentrated sodium hydroxide in the presence of water and sulfuric acid being boiled, is going to yield us a phenol plus sodium sulfate and hydrochloric acid. The third method is by hydrolysis of benzene sulfonic acid. Here we react benzene sulfonic acid with sodium hydroxide, and being boiled is going to yield a phenol and sodium hydrogen sulfite. The next thing we'll be looking at is the physical properties of phenol. Phenol is a colorless hygroscopic crystalline solid. Phenol is a colorless hygroscopic crystalline solid. It is poisonous and has a characteristic antiseptic smell. Phenol has significantly higher melting and boiling point and greater solubility than the corresponding alcohol. That is, for example, if you have to compare cyclohexanol and phenol. Also, we can compare phenol and alkanes of comparative relative molecular masses. We see that phenol has a significantly higher melting and boiling point and also a greater solubility than corresponding alcohol and alkanes of comparative relative molecular mass. This high melting and boiling points with greater solubility in phenol is due to the increased polarity of the hydroxide bond in phenols. Is due to the increased polarity of the hydroxide bond in phenols, which produces stronger hydrogen bonding than cyclohexanol and alkanes of comparative relative molecular mass. Phenol is a stronger acid than water, whereas aliphatic alcohols are weaker acids than water. This is because electrons of the oxygen are drawn into the pi system of the benzene ring, and this makes phenol acidic. As a result of the polarity of the hydroxide bond, there is a loss of the proton to form phenoxide ion. There is the loss of a proton to form phenoxide ion. This is because electronegative charge. This is because the negative charge in the phenoxide ion is delocalized around the benzene ring, but aliphatic alcohols do not show this behavior in solution or with aqueous bases because the negative charge remains localized on the oxygen atom. Due to the overall electron withdrawing effect of hydroxide group, the aromatic ring in phenol is much more reactive towards electrophilic substitution than the benzene ring. This may be shown in various ways. The same reaction occurring more rapidly, more substitution taking place under same conditions, less vigorous conditions being required for the same reaction. Next thing we'll be looking at is reactions of phenol. Phenol undergoes 3 types of reactions. The first is formation of phenoxide. That's formation of the phenoxide ion. As an acid, phenol reacts with reactive metals in bases to form phenoxides. For example, we have the phenol reacting with sodium hydroxide to form sodium phenoxide and water. Sodium phenoxide reacting with chloroethane to give ethoxybenzene. The ethoxybenzene that you can see there is being formed. The phenoxides, that is what we're saying here, is if these phenoxides are reacted with halogenoalkane, they form ethers. As you can see there, that's an example of an ether, ethoxybenzene. The next reaction is the formation of esters. Because phenol is acidic, it does not react directly with carboxylic acid to form esters. It reacts only with acid chlorides and acid anhydrides to form esters. As you can see there, phenol reacting with ethanoid chloride to give phenylethanoate and hydrochloric acid. Phenol reacting with ethane acid anhydride to give, is going to form the phenylethanoate. It's going to form phenylethanoate. ethanoate and methanoic and ethanoic acid. And ethanoic acid. The reaction is faster in an alkaline. The reaction is faster in an alkali, which readily forms phenoxide ion, which then reacts with the acid chloride or acid anhydride to form the esters. The next we'll be looking at is a ring substitution, the ring substitution of phenol. Phenol undergoes electrophilic substitution reactions, and the first we'll be looking at is halogenation, where phenol reacts with aqueous chlorine or bromine at room temperature to yield a halogenated phenol. No catalyst is needed. As in the reaction, you see chlorine reacting with phenol, that's aqueous chlorine, at room temperature to yield 2-chlorophenol. And also, in excess halogen at room temperature, tri-substituted product is yielded. You can see phenol reacting with excess aqueous chlorine at room temperature yields 2,4,6-trichlorophenol. We said the product is 2,4,6-trichlorophenol. Compare this with benzene, where liquid chlorine or bromine and a halogen carrier are required in the reaction, yet produce only a mono-substituted product. The next reaction we'll be looking at is sulfonation of phenol. Phenol reacts with concentrated sulfuric acid at room temperature to yield hydroxybenzene sulfonic acid. Like you can see there, that is our hydroxybenzene sulfonic acid produced alongside with water. Comparing this sulfonation of phenol with the sulfonation of benzene, where in the sulfonation of benzene, a temperature of 35 to 50 degrees Celsius is needed for the reaction to occur. The third reaction there is the nitration of phenol. In the presence of dilute nitric acid, phenol is nitrated at room temperature to produce a mixture of 2 or 4 nitrophenol and water, like you can see them. However, when a nitrating mixture is used, 2,4,6-trinitrophenol, the explosive picric acid is produced. As you can see, 2,4-trinitrophenol is produced in the presence of a nitrating mixture. Comparing this with benzene, where heating with a mixture of concentrated nitric acid and sulfuric acid is required for single nitration. Also, we have to look into the case where we see that the 2 or 4 nitrophenol are isomers. That is 2 nitrophenol and 4 nitrophenol. These two compounds are isomers of nitrophenol, and they differ in physical properties. The closeness of the hydroxy group and nitro groups in 2-nitrophenol results in intramolecular hydrogen bonding, while in 4-nitrophenol, intermolecular hydrogen bonding is common because the functional groups are inside. That is, the functional groups are wide apart. As a result of this intra and intermolecular hydrogen bonding in 2-nitrophenol and 4-nitrophenol respectively, 2-nitrophenol has greater solubility and lower boiling and melting point, while 4-nitrophenol has lower solubility and higher melting and boiling points. 2-nitrophenol is easily separated from 4-nitrophenol by steam distillation. That is, phenol can reduce. That is the fourth reaction of phenol, the reduction reaction. How can phenol be reduced? Phenol can be reduced to cyclohexanal using nickel and an acid as catalyst. Like the first reaction we see there, phenol in the presence of nickel catalyst and hydrogen acid as catalyst. In the presence of heat, is going to give us cyclohexanol. When phenol is distilled with zinc dust, it produces benzene and zinc oxide. Like you can see the second reaction there. Now we're going to be looking at the test for phenol. Phenol reacts with aqueous neutral ion 3 solution to give a purple or violet complex. We've come to the end of our aromatic alcohols. The next compound we'll be looking at is ethers. Ethers have the general formula. As you see, R1 attached to the oxide group, then to another alkyl group, R2. That's R1 or R2. Where R1 and R2 are alkyl or aryl groups. If R1 equals R2, then it is a simple ether. But if R1 is not equal to R2, then it is a mixed ether. Simple ethers are symmetrical, while mixed ethers are unsymmetrical. Like you can see, example of simple ethers which are symmetrical, we have phenoxybenzene. Also, an example of simple ether again is methoxybenzene. Looking at our mixed ethers, which we say mixed ethers are unsymmetrical. We have examples there such as phenoxymethane and methoxyethane. There are also cyclic ethers which contain the oxygen, which obtain the oxide bonding in a ring or cyclic structure. Cyclic ethers collectively called epoxides. That is, cyclic ethers are collectively called epoxides. Example, epoxyethane. And the next example we see there is trimethylene oxide. Ethers are regarded as alkoxy derivatives of alkanes or aryl nucleus. An ether consists of two single covalent bonds, each joined to a separate alkyl or aryl group. The most important ether is ethoxyethane. This is a structure of ethoxyethane. As we go further, we'll be seeing it. Now, we're going to be looking at the preparation of ethoxyethane. Ethoxyethane can be prepared by refluxing sodium ethoxide with chloro or bromoethane. Refluxing sodium ethoxide with chloro or bromoethane, like the reaction below, refluxing sodium ethoxide with bromoethane is going to yield us ethoxyethane. And the second method we can obtain ethoxyethane is by partial dehydration of ethanol using concentrated sulfuric acid at 140 degrees Celsius. As you can see on the reaction there. And the third we'll be looking at is we're going to be looking at now the physical properties of ethers. Ethers are generally unreactive and are mostly used as solvents. They have low boiling and melting points than alcohols, since only weak van der Waals forces exist between them. But hydrogen bonding exists between alcohol molecules. Ethers and alcohols show functional group isomerism. For example, The formula below has the following isomers: methoxymethane and ethanol. In our next lesson, we're going to be looking at carbonyl compounds. And we say carbonyl compounds are aldehydes and ketones. We'll be looking at their physical properties, their preparation, and their reactions. Thank you, and see you next lesson.